All right, this is Mr. Moser. We're going to do an online review. Actually, more it's a summative review. We're going to cover forces, we're going to cover momentum, we're going to cover energy, and we're going to cover circuits. So the last 4 units that we covered leading up to the summative. You should have an equation sheet with the equations for those 4 units embedded onto that. So remember, a long time ago we talked about forces, and in forces we first discussed that basically a force is an interaction between 2 or more objects, and forces basically are pushers and pulls. We talked about Galileo and how Galileo developed some ideas about inertia and how inertia and mass are related, in fact directly related. And Galileo presented this idea of dropping a ball from a certain height, like this ball here. And when you release that ball on a surface, it'll roll down and come back up the other side. In fact, assuming there's no friction, it'll come back up to the exact same height on the other side. He then proposed, well, what happens if we change the angle of the second half of the board? Then the ball will go down and come back up. Again, he says it will go back up to the same height. So then he says, well, let's pretend that we now straighten the other side so it never comes back up. And he asks the question, how long will that ball roll for? And what we learn is that it will roll forever. Forever is a long time. Basically what he was meaning is that objects have inertia, and inertia is that property of matter that resists changing its motion. And so Newton's first law, which was developed after this idea of Galileo, is that objects at rest stay at rest, and objects in motion stay in motion. This is known as the law of inertia. Okay, so Newton's second law was how acceleration is related to force and to mass. So acceleration, force, and mass. We learned that acceleration and force are directly related. So if I take a force and I push this box, the box with more force, the box will have more acceleration. Force and acceleration are directly related. And we learned that the bigger the box is, a more massive box, it will have less acceleration. So we learned that acceleration is proportional to 1 over mass. In other words, they're inversely proportional. Hence, we put these 2 equations together and we are able to come up with Newton's second law. Acceleration is equal to force over mass, or more commonly known as force equals mass times acceleration. Sir Isaac Newton's third law. For every action, there is an equal and opposite reaction. Action, meaning an action force. Reaction, meaning a reaction force, not an effect. For example, if we have an action force, if you look here, the action force is the rock pushes on the gas. The rocket pushes on the gas. The reaction would be the gas pushes back on the rocket. Hence, the rocket is propelled forwards. Let's look at an example over here. Action force is the earth pulls on the ball down. You can see the arrow indicating down. So the reaction would be the ball pulls on the earth up. And a third and final example, we have they want to know what is the action force. If the reaction is the spring pulls on the man, the action force would be the man pulls on the spring. So remember, for Newton's third law, action, reaction. Let's also remember that the amount of force in the action-reaction is equal. So one of the examples we did in class, if you guys remember, we talked about this little butterfly. And remember we had that speeding car in class? And that butterfly gets hit by that speeding car in class. And when they collide, the force that the butterfly feels is in this direction, and the force that the car feels is in this direction. The car gets hit by the butterfly in one direction, and the butterfly gets hit by the car in the other direction. And those forces, these forces are equal and opposite. Now, speaking about forces, mass and weight is something that we strongly emphasize. There is a difference between mass and weight. Weight is simply mass times the gravitational acceleration, which is usually 9.8 if you're on Earth. And mass is the measure of inertia, or how much stuff an object contains. So don't get those confused. They are related by this equation, but they are not the same. Notice the astronaut here has a mass of 120 kilograms, but he weighs 12,000 newtons on Earth, and the mass of the same astronaut, 120 kilograms on the moon, but it weighs only 200 newtons. Moving on to net force. Net force is defined as the sum of all the forces acting on an object. And so if we have an object here, we might have up and down forces, we might have left and right forces. If we add up all the up, down, left, and right, then we will have what is called the net force. If an object has a net force, then the object will accelerate, according to Newton. So let's look at an example. An applied force of 200 newtons is used to accelerate an object with a weight of 80 newtons to the right across the frictional, with friction, surface. The object encounters 30 newtons of friction. So to fill out one of these charts, we would first identify what is given. 200 newtons is the applied force. 80 newtons is the weight. Remember that weight is mass times gravity, and weight had the symbol force of gravity. And the frictional force was 30 newtons. So now our job is to basically fill in these other four missing parts. So first we can recall that if the object is not accelerating in a direction, then the forces will be balanced. And so I know that these two forces will be balanced because this object is accelerating, but it's accelerating to the right. And so I can fill in the normal force being 80 newtons because it's equal to the weight force. Next, I'm going to try and find the mass. And if you look at your mass equation, it's the force of gravity divided by the acceleration of gravity. In this case, it would be 80 newtons divided by 9.8. So that is 8.16. Next, I'll find the net force, and I can do that either by calculating force equals mass times acceleration, but I don't know the acceleration yet, or I can add up all of these forces up here. Remember, if they're opposite, they subtract each other. And if they're in the same direction, they add. So these two are opposite and they are equal, so they subtract and cancel to 0. And the applied force is opposite the frictional force. And you can see it's 230, so the difference is going to be 170. And that's going to be your net force. To find the acceleration, we use the equation. Acceleration is the force net divided by the mass. We would take 170 being the net force divided by 8.16, and we get 20.8 meters per second squared. And that's how you complete the net force chart. When we deal with conservation of momentum, we need to first find the momentums of both buoys before and after the collision. And if you recall, we talk about the momentum of an object before a collision is equal to the total momentum of the objects after the collision. And this is what we mean by conservation of momentum. So let's look at an example here. Running at 2.5 meters a second, Andrew, the 50-kilogram quarterback, collides with Ian, the 80-kilogram tackle, who is traveling in the 6 meters per second in the opposite direction. This is going to be key. Upon collision, Ian continues to travel forward at 1 meter per second. How fast is Andrew knocked backwards? So let's go ahead and look at this for a second. So we have 2.5, we have 50 kilograms, we have 80 kilograms, we have 6 meters per second in the opposite direction, and then we have Ian traveling 1 meter per second. So we set up our equation. The momentum before equals the momentum after. And then we might ask ourselves, what kind of collision is this? So what kind of collision is this? It's an elastic collision because they hit and bounced off. So the equation is m1v1 plus m2v2 equals m1v1f plus m2v2f. And now we need to identify all those letters. And let's go ahead and do that over here. We have Andrew has a velocity right here of 2.5, so v1 equals 2.5 meters a second. We have Andrew, so m1 equals 50 kilograms. We know Ian is m2, and he's 80 kilograms. And he's traveling v2 equal to negative 6 meters per second. And we also know afterwards Ian, v2f, equals forward positive 1 meter per second. So we've identified our givens. We can see that we're missing how fast Andrew is moving after, which is our v1f, which is exactly what we're trying to find. So we will plug our numbers in and chug through the answers here. So m1, 50, times v1, 2.5, plus m2, 80, times v2, negative 6, equals m1, 50, times v1f, which we don't know, plus m2, 80, times v2f, which is 1. So 50 times 2.5 is 125, plus 80 times negative 6 is negative 480, equals 50 times v1 is just 50 times v1 still, plus 80 times 1 is just 80. So 125 plus negative 480 is a negative 355, equals 50 times v plus 80. And solving for v, I'm going to subtract 80 on both sides. This becomes negative 435 equals 50 times v, because the 80s cancel out. Now I'm going to divide by 50 on both sides, and I end up with v equaling negative 8.7 meters per second. So how fast did Andrew get knocked backwards? The answer is negative 8.7 meters per second. That was an elastic collision. You will definitely be expected to solve a collision problem, elastic, inelastic, or possibly explosion. We also talked about impulse momentum theorem. What is the momentum of an object? An 8 kilogram object, kilogram bowling ball rolling 2 meters a second, so that shouldn't be a problem here. Momentum is equal to mass times velocity, so that'd be 8 times 2, or 16 kgm over s. The next question is, if the bowling ball rolls into a pillow and stops in 0.5 seconds, calculate the average force. So here we're going to use the impulse momentum theorem, which basically states that the impulse on an object, which is force times time, is equal to the change in momentum of that object. And so we can say that the force times time here is equal to the delta P, and since the object had a total of 16 kgm over s before the collision and after had 0, we can say that the delta P is equal to negative 16. And we can plug in for time. Force times 0.5 equals negative 16. Dividing both sides by 0.5 tells us that the force is equal to negative 32 newtons. So there's our answer to question 2. Now let's go to question 3. Oh, I guess I answered question 3. What average force is exerted on the ball? Well, since the force on the pillow is negative 32, the force on the ball would just be positive 32, because Newton's third law tells us they're equal and opposite. Okay, so we talked about energy. Energy cannot be created, cannot be destroyed. It can be transferred if you do some work, and it can be transformed if you keep it within the system but change the energy type. Let's look at an example. A load of bricks rests tightly on a coiled spring, then is launched into the air. Assume the system is the spring, the bricks, and the earth. Do this problem without friction. How much energy is in the spring? So we can say, well, at first the energy is not, there's no movement and there's no height, and so all the energy is in the spring. And all that energy then gets flung from the spring, is put into the box, and the box is now lifted up to a certain height. And so we can say the box being at the new height has no velocity, so it's got no kinetic. The spring has lost all its energy, so it's got no elastic, there's no friction. All the energy is turned into potential energy. Now we can write the equation for conservation of energy, which states that the energy in position A has to equal the energy at position B plus or minus work that comes in or goes out. There's no work going in or out, so it's just the energy at A, which is EE, so elastic energy, is equal to the gravitational potential energy. The question is how much energy was in the spring, and so we know the energy in the spring is equal to the potential energy that the object has after. So we can calculate the potential energy because we know the equation is m times g times h. So the spring energy will equal mass times gravity times height. The mass of this object looks like it's not given, so let's just give it a mass real quick. Mass is 2 kilograms. So the mass is 2 times gravity of 9.8 times a height of 10. It tells us that the elastic energy is 196 joules, 196 joules. That's how you calculate elastic energy in this example. So in this next example, we'll just run through this pretty quick. The mass of this car, let's say, is also 2 kilograms. It looks like it's starting at the bottom of a hill, but it has some speed, and it reaches the highest point. Notice the velocity is 0. So it starts with all kinetic energy, and that turns into all potential energy. So EK equals EG. The equation for kinetic is 1/2 mv squared. The potential is m times g times h. And so we can see that the kinetic energy is turning into the potential energy. Let's go ahead and plug some numbers in. 1/2 times the mass, which is 2, times the velocity, 25 squared, equals the mass, 2 times gravity, 9.8, times the height, which we don't know. 1/2 of the mass is now 1 times 25. That's going to be 625. Twice times 9.8 is 19.6 times the height. Go ahead and solve this, dividing both sides by 19.6. So dividing by 19.6 tells us that 31.8 meters is the height of that car. Again, using the idea that energy is conserved, the energy at the beginning equals the energy at the end. More recently we talked about circuits. Here we have 2 examples of circuits. We have a series circuit when the devices only have one path for the current to flow, and here's an example of a parallel circuit. Let's go ahead and fill in the chart for these circuits. Given 24 volts, resistor 1 is 4 ohms, resistor 2 is 6 ohms, resistor 3 is 2 ohms. Since this is series, we know that the current that flows through this circuit passes through each resistor, so the current stays the same. We also know that the resistances will add up, and so the total resistance is 4 plus 6 plus 2, which is 12. Now I can use Ohm's law that tells me I equals V over R to calculate the current right here. V being 24, R being 12, so the current is 2. Current stays the same, so I have 2 for all of the devices. And then using Ohm's law again, V equals I times R, I can find the voltage. 2 times 4, which is 8. 2 times 6, which is 12, and 2 times 2, which is 4. To double check, the voltage that is dropped across each resistor has to add up to the total voltage of the battery, because that's one of the rules for series circuits. 8 plus 12 is 20, plus 4 is 24, which adds up to the total. Now for parallel, remember the difference here is the current that comes out of the battery splits up. Some goes into the first branch, some goes into the second branch. So let's go ahead and fill in what we know. We're given 100 volts. We know that the first resistance is 50, second resistance is 20, and we actually don't have a third resistance, so I'm just going to remove that. To calculate the total resistance, we do 1 over total equals 1 over 1 plus 1 over R2. In this case, it would be 1 over 50 plus 1 over 20. Finding a common denominator, we could use 100. You would multiply this first one by 2, so 2 over 100, and the second one by 5, 5 over 100. We can see that that turns into 7 over 100, and then inverting it, the total resistance then is 100 divided by 7. 100 divided by 7 is 14.3. So again, using Ohm's law, I can say that I equals V over R, where V is 100 and R is 14.3. And that tells me that I have a current of basically 7. Now, in a parallel circuit, the voltage on the battery, which is 100 volts, is the same for both resistors. You see that voltage drop is the same. And so in a parallel circuit, I can plug in 100 for both of those voltages, and then using, again, the equation I equals V over R, I can figure out how much current of the total 7, how much goes in here and how much goes in here. So we're going to take 100 divided by 50, and we're going to get 2 amps, and the leftover amps has to be 5, which you can see 100 divided by 20 is 5, and that's how you fill it out. Good luck in studying for your test, and hope you guys do very well.